Let me start by telling you that for me, air is pretty much the same as water. Now, hearing that, you probably think I'm a bit weird, because there are some obvious differences. Say if you see this picture of a glass of water and you consider the air in this room, they're obviously very different. And luckily, the room, for example, is not filled with water, otherwise we'd all drown. So what I mean with being the same is physics-wise, you can actually look at them in pretty much the same way. And that becomes more apparent if you have something to show how they're moving. So here you can actually see it's just a puff of smoke, actually. And if you look at the shapes that form, if you have something like ink and water, then they're actually very similar, as you can see here. And physics-wise, interestingly, also the same kind of phenomena are driving these shapes and motions. And they're typically summarized as turbulence. So the reason I bring that up here is because turbulence is actually still one of the big remaining mysteries of modern-day physics. And it's actually so fundamental that institutes like this Clay Mathematics Institute are actually paying $1 million for anyone who figures it out. So if you're bored tomorrow afternoon, you might want to give this a thought. Now, you're probably wondering why anyone would pay $1 million for a problem like that. The reason is that it's really fundamental. So starting with the air you breathe, with the plane you take to your next vacation, or also think about what's happening in your body, the blood flowing through your veins, they actually all behave in accordance to these underlying physics. And despite looking very different, we can actually physics-wise look at these materials together, and they're typically summarized as fluids. So that's what I'll also use in the following for these different materials. Now, I personally look at those from a computer graphics perspective. So to show some examples, this is one of our older works a while back where we simulated a kind of burning car and the trail of smoke behind it. And the 4 million particles that you can see in the top right corner, they indicates a bit that there's actually a lot of work going into producing that animation here. Or another example is this truck being chased by a dark cloud of smoke that you can see here. So overall, summary here is these fluids are really important and popping up in many, many situations. So how do we go about kind of working with them or analyzing them? And for that, we can now look at kind of the principles of science. And if you think about how that's been happening way back, for example, with Newton, he was, as the story goes, sitting under a tree, an apple falling down onto his head or beside him is not fully confirmed. But in a way, that was his observation, his data. And from that, he developed these really condensed and nice equations, the model, after which, or with which to model reality here. So those are two really fundamental topics in science, experiment and theory. And coming back to these fluids, they've actually been studied even before Newton was around. So, for example, this is one of the famous sketches of Leonardo da Vinci, where he analyzed or studied the motions of water and the swirls forming. And especially for these, there's actually a third component that's really important. Those are computations. So with computers, we can now actually solve very complicated models and predict what's happening in nature. Now, the reason I'm standing here today is that we have a kind of new kid in town, these deep learning techniques. And I know that's quite a buzzword by now. So you probably heard it too many times recently in the news and everywhere, talking about buzzwords. Here's another one. But I can promise that I won't be talking about blockchains at all. So I'll focus on this deep learning in the following. And in order to understand that, I also want to explain a bit how that works, because what is actually driving pretty much all of the techniques you find summarized as deep learning are what's called neural networks. So those are roughly modeled by our probably quite limited understanding of the human brain. But as the name suggests, it's a network of nodes. So I want to give an example here. This blue dot that you can see here might now be one of these nodes in the network. And we now have some input coming, in this example, from the left, going out on the right. Each of these arrows is actually just a regular number. Now, to make it a bit more interesting, we might have 3 nodes in the next layer here, and then another 3 in the following one, all of those being connected to each other. And to keep it small, maybe everything merges on the right-hand side back to a single one again. Now, if you look at from the larger picture here, we have an input on the far left, and then it goes to the right with an output. And now, let me first explain what happens in one of these nodes. So, if we now look at anyone in that network, in this particular one, we actually have 3 inputs, as you can see here. We typically multiply these inputs with some weights, here shown by these W. We sum them all up, giving us a new number, and that number we actually modify, typically in a relatively simple way, for example, by cutting off the negative part. And then the remaining positive one is sent on to the next node here, in this case, the output. And that's what's happening in all of these nodes. There might actually be many of them, but this is pretty much the same procedure everywhere. Now, the trick here is that we actually collect a lot of in- and output pairs and give that to a computer. And the computer, in the computation step, can now figure out how to set all these weights. So for each of the white arrows here, we have one of these multipliers, how to adjust them so that we get the output as good as possible with that given network. So that is the actual learning step, typically, in these algorithms. And yeah, for that, we actually need data again. So if you think back about the example of Newton, we might go back to observing falling apples. But in this case, actually, it's not enough to see or observe a single one, but typically we need many of them. So ideally, we have millions of data points to use in this procedure. And also thinking about this example of Newton, what now happens here in a way is that this step kind of takes off the theory, figuring out the theory, and does that automatically in this optimization process. So one thing worth noting here is also that it's not something that was recently invented by one of the big internet companies, but it's something that actually comes from many centuries of pretty fundamental academic research that now takes off in a way. Yeah, so hearing about this in the news, you probably have read about the superhuman performances, and one of the particularly good things here is finding cats and dogs in images. So here are some examples where that would work very nicely. And it's wonderful in general because the internet does probably consist to more than 90% of cat and dog images. So it's a great start. However, often it's also mentioned in conjunction with artificial intelligence. And I have to admit, I don't like that label too much. I mean, it's a somewhat philosophical question. What is intelligence? You can think about it as something taking an input and then producing some kind of reaction or output. But here also, you quickly have these connotations of machines turning against us, Terminator style. And when I think about all of these techniques, it's actually more about just representing a function. Really think back to high school, f of x equal to y. In the end, the computer figures out the f here, which might sound very boring at first, but that's actually what makes it very generic, and also powerful, because these deep learning algorithms are actually really better than anything we had before to compute these functions. And with that, I now can explain a bit what I meant with the title. So, going beyond finding cats and dogs and images, I'm, for example, really interested in applying these techniques to these fluid problems. And here now I can show a bit of the research we've been doing in the past years on that topic. And the first one is now focusing on smoke simulations. So what we did here was we looked at first a kind of rough, simple smoke simulation that you can see here on the left-hand side. With the simulation, you can actually produce that pretty cheaply. And then you can invest more time and produce a more accurate version of the same smoke cloud. Here on the right, I hope you can see it has a lot more detail and structure. Now, we looked at windows out of these data sets to make it a bit more generic, and trained one of these deep learning, used one of these deep learning algorithms to give us links or correspondences between these data points. And then also once in the beginning, we actually go in and build a big library of these more accurate versions. Having done that, what we can do is if we now look at a new smoke cloud, for example, this mushroom-shaped one that you can see here on the screen, we can sample it with all these little windows, load the library, and now with the help of this trained network, which now kind of takes the role of a smart librarian to tell us which data sets from the library are the best ones that fit here, and also respect the physics of this input, we can create a version that has a lot more detail and uses the data from the detailed and more accurate version here. I can directly show some examples in motion here. This is now one of the inputs. Hope you can see it's relatively boring, and the version you can see here now has this added detail from this library. Or this version shows them side by side, the input and the more detailed version. Or another example that we simulated were these colliding jets of smoke here. Again, this is the version with very little detail, and the version with all the added complexity from the neural network here. Or side by side again, it's even more obvious. Yeah, so in a way, this now gives us the more accurate behavior in a much cheaper way, and also enables the use of this library. Another example that we looked at were liquid simulations. So here might actually look something like this, a little blob of something like water falling to a little basin where you cannot see the walls. What we're interested here in are actually kind of families of these simulations. So I hope you can see on the picture here that these drops change in size from small to large and also fall in at different positions. And now if I show you the animation for it, it gives you very different behavior. So what's here especially challenging is actually how this behavior changes when we only change the size of this drop in the beginning. And that is what we wanted to capture here. So just to give you a very quick overview, what we looked at were actually doing a fairly expensive pre-computation step, and then again training one of these deep learning algorithms to actually kind of refine the behavior to take into account all the simulation data that we have in this whole space of simulations. And what we get out in the end is actually a representation that is so small that we can run it on a mobile phone. And you can actually try that yourself. If you're interested, you can download the app that I'm showing here, but this is a video of it running. And yeah, you have some additional pillars here around it, but in the middle you can see these drops falling into the little pool at different positions and sizes. And if we actually try to run one of these simulations on the mobile phone, it would probably take more than half an hour, and here it's running with 50 frames per second. So effectively, that's probably a speed of more than 1,000. So it's really a lot faster, thanks to this, thanks to the underlying algorithms. And that kind of hints at the possibilities here. So we get actually very complex behavior very quickly. And as far as we know, it's actually the first time you can actually run such a simulation on a mobile phone. Yeah, and with these examples, I want to take a bit of a step backward again and look at this bigger picture. So I've talked about these different pillars of science, and I now don't want to claim that this deep learning is actually the fourth one or replaces the computational side here, but it definitely will be a very important component within those computations. That's pretty safe to say. And the key message really is that it's something that is not just useful for finding cats and dogs in images, but it's a really generic computational method that influences the work of anyone working with computers, and as such, indirectly also all of our lives in the years to come. So for my field of work, what's especially interesting is actually capturing the behavior of nature around us for virtual worlds, ideally in real time, as realistically as possible. And that starts, of course, with something like a falling apple, but ideally we'd like to look at effects such as the one shown here, which is definitely an extreme example. This is a giant wave hitting a lighthouse. So if we could capture this kind of complexity in a virtual environment, I think that would be really exciting, and there's potential here, I believe. I don't want to pretend that the sky is all blue. There are some definite or clear limitations of these methods still today. One of them, for example, is that these methods can actually not really learn larger context that well, or kind of understand the bigger picture behind the data. So that is something we definitely will need to work on and that we'll need to improve in the future. But whether we do that or not, I think it's already very powerful. And ultimately, of course, the goal here is also to better understand the physics behind it, not just display them, but I think these methods can actually help us understand what is happening. And one area where I think that is especially important and interesting is actually the human body. So if you think about the flow happening in your heart, it's actually an extremely complicated one. And if we had methods there to quickly and accurately predict what the blood flow in a patient's heart is, that would be something that is really very useful for, potentially very useful for medical doctors and could potentially save many lives. So I think this is a particularly interesting direction for future work. Yeah, and I want to close with a quote from Picasso that I found. He actually more than 50 years ago said that computers are useless because they can only give us answers. In a way, I think that's still very true today. So the interesting challenge really is, how do we pose the right questions? So in particular, how can we actually set up questions such that these deep learning algorithms give us answers that we can use and work with? And for me specifically, I'm really interested in how can we set up these questions for the computer such that we get answers about things like turbulence and understand it better. And I think there's actually a lot of very interesting work left. So in a way, exciting times for research. And yeah, with that, I want to thank you for your attention. I also quickly want to mention this is, of course, based on work of my students, so especially Rachel and Lucas worked hard on the topics I showed earlier. And if you're interested in trying this, we have this app called Neural Liquid Drop. If you want to try these droplets or real-time liquids yourself, feel free to try. Thanks.